Hi guys, I'm Chen and I am going to talk about pre-trained models for today's lab session. So for the outline, we're going to talk about what the pre-trained models are and why we need them, how we obtain them, and some tips on how to use pre-trained models, and also some example that we're familiar with. So, what are the pre-trained models? A pre-trained model is a neural network model that has been trained on a large data set whose learned parameters that can be reused. Remember that the main objective of training is to get a set of parameters, which, when used, result to a mapping of an input to an output with minimum error. So here we already have our parameters, which we would like to reuse. For example, one of the popular examples is that ResNet 50 model like that could be trained on ImageNet with a huge data set with like approximately more than 1 million images across 1,000 categories, and then can be shared so others can use it without training it from the scratch with such large data sets. And characteristics of pre-trained models are, first, they have prior knowledge. They already have learned general features such as edges, shapes, textures, or in language model, grammar or context from vast data sets. And this knowledge serves as a foundation for new tasks. Second, there are weights that's saved, so it can be reused. They can be reused. The parameters are saved after the initial training and can be loaded to initialize a model. And third, last but not least, that it is open source. Most of them are openly available in model zoos or libraries such as PyTorch, Hugging Face Hub, or TensorFlow Hub. Transfer learning is the practice of taking a pre-trained model and adapting it to a new but related task. This concept is important because it allows solving a new problem by reusing what the model has learned on a related problem. For example, back to ResNet, a ResNet model that's trained on 1,000 categories, and using the same model, we can classify fewer categories of a different domain. And the second part of the lecture today, why do we need them? Why do we need the pre-trained models? What are the benefits? So first, it reduces the training time and cost significantly. As you guys already know, from all the homework experiences, training a deep neural network from scratch can be really time consuming and resource intensive. Replicating a modern CNN on ImageNet from scratch might take days or sometimes even weeks on a powerful hardware, and that's why we can skip this process and save time with pre-trained models because the model already converged on a larger data set. The second reason is that it performs better on small data sets. In your workplace or research, it's kind of hard to have very large data sets for every single task. Pre-trained dataset come into handy to give you a comfortable performance on a small set of data. The model has learned general features from a big dataset, usually larger than what you need to use, and can apply them to your problem. As a result, models fine-tuned from pre-trained weights often outperform those trained from scratch on smaller datasets. Third, we can avoid overfitting by using pre-trained models. Initializing with pre-trained weights can act as a form of regularization. The model's parameters start in a good place that encodes general knowledge rather than random values. This often means that you need less data to train effectively, and you're less likely to overfit the small training set you have. Fourth, feature extraction. Even without fine-tuning, pre-trained models can be used as feature extractors. Early layers of CNN learn very generic features such as edges, colors, basic shapes in terms of image data that are useful for many tasks. But you can freeze the convolutional base of CNN and use it to transform raw images into feature vectors and then feed them to a classifier. Last is benchmarks. You can, sorry, oops, sorry. You can benchmark models, um, like popular pre-trained models that I'm going to introduce later, such as ResNet, BERT, or T5, even GPT. They are often well tested and validated. So using them gives you a reliable starting point with less hassle. So how do we get them? Where do we get them from? There are many sources of pre-trained models. The first is PyTorch. Everybody knows about PyTorch, so I'm gonna explain it very briefly. Um, but PyTorch has libraries such as TorchiVision, from which you can access pre-trained models on. It also offers a broader model hub, such as Torch Hub, for models contributed by the community, including NLP and audio models. Second is Hugging Face. Hugging Face hosts hundreds of thousands of models contributed by the community and organization. The Hugging Face Hub is a rich resource, not just for models in PyTorch, but also TensorFlow, Keras, and ZX. Third, although we use PyTorch for our assignments, as I mentioned earlier, it also offers actually never mind, this is TensorFlow. So yeah, although I mentioned PyTorch earlier, um there's TensorFlow which we don't often use, but it also offers an open source repo of pre-trained models. You can check out TensorFlow Hub to load and reuse these models in TensorFlow or Keras. Fourth, there's Open Neural Network Exchange. It's an open format to represent models. The zoo is a collection of pre-trained state-of-the-art models in the ONNX format. And these models can be used across frameworks that only support ONNX. Um, the model zoo also includes vision models, like for classification or detection, and NLP models, of course. Last but not least, Kaggle, which we are very familiar with. They have a section for pre-trained models actually, and it's called like Kaggle kernels or models, where community members share their models they've trained, including the weights. We'll also let you explore this by yourselves since you're already familiar with the territory. Fourth, tips on using pre-trained models. How can we take an advantage of pre-trained models? How can we use it wisely? First, you have to understand the source data set. Pre-trained models are typically trained on large data sets like ImageNet or large text corpora. Understanding the source data set helps you gauge whether the model's learned features are transferable to your cat task. Also, ensure that your input data matches the format and pre-processing steps used during the model's original training, such as resizing images, normalization of pixel values, etc. Second, leverage transfer learning. It can be parameter efficient. It basically means to start with a smaller learning rate. Fine-tuning a pre-trained model requires careful learning rate tuning. A small learning rate will ensure that the pre-trained weights are preserved while you adapt the model to your data. Third, choose the right model for your task. Consider the type of data as well. Consider model size and complexity. Because pre-trained models come in various sizes. For example, like if we go back to ResNet, there's ResNet 18, 50, 152. You have to choose a model that balances accuracy with performance of your task. Fourth, use pre-trained models as primary feature extractors. Freeze lower layers. You can use pre-trained models as feature extractors by freezing the lower layers and only training a small classifier on top. This is helpful when you have limited data and still want to use the model's learned feature. Last, experiment with different fine-tuning strategies. It basically means that to freeze the layers based on task similarity. For example, if your task is very similar to the task the model was originally trained on, for example, if you're using the ImageNet pre-trained models and you're using that model for image classification, then you might only need to fine-tune the final classification layers, but for dissimilar tasks, you may need to fine-tune more layers. These are just like five, but few tips of using pre-trained models. And there are so many other tips that you need to consider and you will come to interact with as you continue experiencing and exploring the models more and more. Remember that in this course, in any homeworks, we do not use pre-trained models ever. The purpose of this is so that we learn how to tweak model and understand what it is to build a model from scratch. So we're going to explore a little bit on popular existing pre-trained models. Hmm. First is BERT. I am sure everybody here knows about BERT. It came from Google in 2018 and changed natural language processing by introducing bidirectional context, meaning that it reads text from both left to right and right to left at once. Before BERT, models mostly looked one way, like reading with one eye closed. By pre-training on massive text corpora with tasks like masked word prediction, Bird learned language representations that could be fine-tuned for many downstream tasks, such as question answering, sentiment analysis, even scientific paper classification. And then the GPT came. OpenAI flipped the direction. GPT is not bidirectional, it is unidirectional, but it focuses on generation. Instead of filling in blanks, GPT learns to predict the next token in long sequences, which makes it strong at producing coherent text. If I wanted to explain it like comparing to BERT, while BERT is good at understanding, GPT is more specialized in creating. That is maybe also why it's called generative AI. And as model size grew, it picked up like emergent abilities such as reasoning, coding, and even stylistic mimicry. It is a good reminder that the same transform architecture can express very different capabilities just through its training objective. Next up is T5. Google's text-to-text transformer, a transformer, tried to unify everything. Rather than juggling different model heads for classification, translation, or summarization, T5 reframed all NLP tasks as text in, text out. That single design data, every problem becomes text generation, simplified pipelines, and made pre-training and fine-tuning more consistent. It also demonstrated how scaling model size and dataset diversity systematically improves generalization, an insight that still drives today's large language model trend. And the next, ResNet, that we've been talking about. Its full name is Residual Network, as you know. It came out of Microsoft research in 2015. It solved the vanishing gradient problem by adding skip connections, basically letting information and gradients flow through shortcuts. It also allows different sizes, like we said earlier, 50, 18, or even 152 layers. It became the foundation for nearly every visual backbone that followed, from like medical imaging to like robotics and anything else. And finally, YOLO. It's not you live only once, it's you only look once. It reframed object detection as a single stage regression problem. Instead of scanning an image multiple times, this model predicts bounding boxes and class probabilities in one shot, making the image detection real time. It is very fast and fast enough to like autonomous driving or like live video analytics, so it is very widely used. So across these examples, BERT, GPT, T5, ResNet, and YOLO, we see kind of like a pattern. Pre-training distills broad knowledge and fine-tuning tailors it to specific goals. Each model captures something fundamental, like BERT taught context, GPT taught generation, T5 task unification, ResNet could be teaching depth, or YOLO being like very efficient. It captured something different, like a fundamental, but all different. So from here, we see more vividly what the characteristic of pre-trained models is and how we can benefit from it. Thank you.